Ubiquitous computing. Coined by the Xerox Palo Alto Research Center's Computer Science Laboratory, this term describes a vision of the future. Just as electric motors have disappeared into the background of everyday life, PARC scientists envision a future where mobile computational devices will be similarly transparent. Potentially numbering in the hundreds per person, these devices are nothing like you use today. They are mobile. They know their location and they communicate with their environment. They can be active or reactive, changing their computation based on their current location, their environment, and external events such as timers, alarms, and sensors. The seeds of ubiquitous computing, also known as Ubicomp, have been planted by PARC's Computer Science Laboratory and are composed of 3 classes of devices. Yard-sized devices span 18 inches to 6 feet. Foot-sized devices range from 6 to 18 inches. And finally, inch-sized devices are 6 inches and smaller, and can be embedded in furniture, light switches, and other objects. The PARC tab belongs to the inch-size class of Ubicomp devices, and is the smallest built at Xerox PARC. It is a pen-based graphics terminal that uses an infrared network for its communication. The tab design emphasizes communication over local processing power for 2 important reasons. First, wireless communication is critical for mobile computing. It allows users to seamlessly connect to the information infrastructure being built from existing wide-area networks. Second, and more important, it is the physical size of the device. The Computer Science Lab's premise was that the tab had to be small enough to enable researchers to carry it throughout the day. However, this requirement placed severe constraints on both the amount of local computation as well as the battery life that could be built into the device. As opposed to designs used for other personal digital assistants, CSL took a novel approach to integrating the tab's communications and size requirements. The result is a PDA that runs a simple operating system and functions more as a terminal than as a workstation, with its applications running on remote hosts. CSL researchers knew that a terminal-based system had clear advantages in its simple design, small size, and low power consumption. The PARC tab infrared packet network is effective for communication between stationary base stations and mobile systems, as well as for communication between 2 or more mobile systems. PARC's IR network was specifically designed for use inside a building, where each room is wired with a transceiver that acts as a communication cell. This design provides seamless communication when a PARC tab moves from cell to cell. Originally built for the PARC tab, the network also accommodates other portable computing devices, such as M-Pads and the HP 95 Palm-Top PC. The PARC tab system software is built from 3 types of processing components: gateways, agents, and applications. Gateways implement a datagram service for sending and receiving IR packets. Each tab is represented by an agent. Independent of the tab's location, the agent provides remote, reliable procedure calls. Agent protocols can be used to enforce security, for example, preventing an unauthorized application from taking control of a tab. The agent also mediates access to the tab. The agent receives application requests bound for its tab and delivers events from the tab to the current application. Applications are built using a library of widgets designed to accommodate the PARC tab's low IR communications bandwidth and small display area. A distinguished application, the shell, permits a tab user to start any application and to switch among them. The system employs 3 communication media. Infrared is used for packets between transceivers and tabs. A serial line connects a host running the IR gateway to the hardware transceiver. Finally, Ethernet connects the IR gateway processes with tab agents. Sun RPC is used for communications between gateways, agents, and applications. The tab shell provides a graphical user interface for starting and controlling tab applications. Tapping an active area on the screen, either an icon or text field, initiates a shell action such as starting an application or moving to a new screen. Once an application has been started, it takes control of the tab. Any pen or button events from the tab are sent to the active application via the agent. Only one application can write to the tab's display at any given time. The middle button signals an application to suspend itself so that control returns to the tab shell. The weather application provides an up-to-date weather report for the area near PARC. It reads the temperature and wind speed from PARC's rooftop weather station and retrieves a timely National Weather Bureau forecast from an internet service. The stylus interface allows the user to scroll through the text of the forecast. The dictionary application demonstrates access to a database that does not fit on the tab itself. By tapping on the keys of a graphical keyboard, the user moves through a word list in a manner similar to Emacs's incremental search function. Tapping on a word in the word list retrieves its definition from a network-accessible dictionary. The calendar application allows access to the user's online calendar. The top button reviews appointments for a given date. The bottom button adds a new appointment for the given date and time. Again, text is entered by tapping on the graphical keyboard. Hand printing recognition is an alternative method for entering text. CSL is experimenting with a radically new script called unistrokes, where each character is represented by a single stroke, which is faster to write and easier to recognize than a conventional character. Unistrokes enables a style of text entry where characters are written one on top of the other. This technique allows the PARC tab to compete with larger devices where each character is normally written sequentially. The tab incorporates a Unistrokes trainer application, providing the user with an easy way to learn the Unistrokes script. The strokes are grouped into classes based on the degree of difficulty in remembering the stroke. Each class is tested separately. The user is presented with a letter and responds with the appropriate stroke. Should the user make a mistake, a correct sample stroke is drawn. Future applications are planned that will allow multiple tabs to collaborate simultaneously using groupware currently under development. The MPad is one of the foot-sized devices in the UbiComp environment. The purpose of the MPad project was to build a device which could create the illusion of having a portable wireless tablet computer containing all the computational power of a workstation. For this illusion to become reality, CSL chose to separate the computational engine from the portable display device. The reason behind this is evident. Separating the engine from the display device means tremendous gains in the power-to-weight ratio. It also enables the computationally intensive tasks to match the speeds of today's powerful workstations, instead of settling for what is currently available in low-power portable devices. This system consists of three key hardware components: the MPad, a portable tablet computer, the radio base station, which bridges the wireless and wired networks, and the near-field radio, which provides the wireless communication. Highlighting the input-output capabilities of the MPad are a 1 megabit per second tether, a built-in 9600 bit per second infrared interface, a 250 kilobit per second radio port, a tethered stylus with microphone, a built-in speaker, one PCMCIA slot, an RS-232 port, and a keyboard port. Linking the radio network with the rest of the building are the base stations. Each base station has an Ethernet port, a 250 kilobit per second radio port, and two MPad battery charging tether ports. The near-field radios are the wireless data link. Each radio operates at 5 MHz and has cells with a 3 to 4 meter radius. The result is office-sized radio cells with very well-defined cell boundaries. The heart of the MPad software architecture is a split X server. The protocol portions of the server run on a workstation, while the graphics engine runs on the MPad. Communication between the two halves of the X server takes place using TCP/IP streams. Let's trace the path of a pen event from the MPad to the corresponding application. The pen event goes into a TCP stream where it is converted to an IP packet. This packet is then sent over the radio under the control of a media access protocol layer to ensure delivery at the receiving radio base station. The base station receives the packet and routes it to the Ethernet, bound for the host side of the X server. The host X server processes the event and notifies the client software. The client software responds to the event by notifying the X server. Packets then travel in the reverse direction from the client to the X server, over the Ethernet to the base station, out the radio, and finally back into the MPad radio. What happens when an MPad moves out of range of one radio cell and into another? The radio base station simply adjusts the routing information so that communication with the MPad is continued under the new base station. The MPad's IP address stays the same, allowing the existing connections to remain intact. This enables the MPad to travel from cell to cell without any interruptions in its communication path. For mobile computers and shared drawing tools, the last decade has been one of evolutionary growth. But ubiquitous computing in the MPAD brings them together, for the first time enabling a revolutionary change in work practice.
Here's what I've drawn for the animated section. It's an MPAD, a base station, and a workstation. See anything you want to add to that?
Well, we could add a second pad to show that there isn't a one-to-one correspondence between pads and base stations. I know. We could put it on a tether.
Yeah, I think that might work.
What are you guys working on?
It's the animation section of the MPAD video. Can you think of anything we might need to add to what we've got here?
Well, perhaps we can add a base station here and a radio. To show that the MPAD can roam between base stations.
Definitely. Seamless, uninterrupted communication is an important issue.
How's it going?
Oh, hi, Ron. Well, we've added an MPAD tethered to the first base station, and we've added a second base station to animate roving. You see anything you might want to add?
Well, that looks pretty good, actually. But I know Bob had a few ideas. He's still busy hacking away for the demo, but we should be able to reach him. Bob, this is Ron. Are you around?
Hi, Ron. What's up?
Hey, we're working on the MPAD animation right now. It's all up on WB. Is there anything else you wanted to add to it?
Let me see. Let me take a look. How about adding a second pad out here, maybe at a remote location, and it could show off the audio features of the pad.
Okay, nice. That emphasizes that the pads don't have to be co-located for sharing.
Thanks a lot, Bob. Okay, I got to run now, but I'll keep WB on and monitor your progress.
Sounds good. Talk to you later.
Okay, looks like we've got it. I'd like to keep this WB session around so that we can come back to it later. But right now I think I'd like to move away from the animation segment and work on the meeting segment for a while. It'd be nice if we could...
PARC's ubiquitous computing vision includes several devices. The liveboard, MPAD, PARC tab, and active badges are key components in this wireless revolution. This vision brings you more than remote collaboration and shared drawing. You have the power of your workstation and a tablet computer. You have unlimited freedom to change your location as the wireless communication infrastructure connects you from one base station to another. Physical boundaries disappear as your computational boundaries and power expand. Pieces of the ubiquitous computing puzzle are coming together at universities and research centers worldwide. At PARC's Computer Science Laboratory, the ubiquitous computing revolution has begun.